As you can see, when you unbind circle from the red circle, you get back red. And when you unbind red, you get back circle. You've now created hypervectors, you've computed their similarity, and you've used binding and bundling to construct objects. So let's briefly compare and contrast what binding and bundling do. Here we'll take two vectors and we're going to pretend that these images, the cat and the penguin, are vectors. And if we bundle them together, we create a new image that is a superposition of the two. The bird and the cat pictures are superimposed, but you can still see that there is some similarity between the superposition and the two elements that make it up. However, here we see what happens when we bind these two images together. As before, our binding is provided by circular convolution, and this new image is not recognizably composed of either of its constituent parts. But now we can unbind this image. For example, we unbind the cat and we get back something that looks maybe like a very blurry version of the penguin, in as much as that there's this large black blob here that roughly corresponds to where the body of the penguin is. Picture. Likewise, if we unbind the penguin, we get back a white blob, roughly where the body of the cat is in its original picture. Obviously, this is not a perfect reconstruction of the images that went into the binding process, and one of the ways that we deal with this is by using a cleanup operation. A cleanup operator removes noise that's accumulated in a vector that arise from approximate implementations. The implementation is approximate because we implement things using spiking neurons, or because we have created noise by applying multiple approximate operations like the pseudo-inverse. So cleanup takes the noise out of the vector and gives us back the original vector or something close to it. There are many ways to implement cleanup, but what we're going to use today is going to look like a modern Hopfield network. Let's try an experiment with that now.